Hi there, this is Ariel NY4G, and the topic for the video today is simple wire antennas and why 50 ohms. This video is meant to be a follow-up to the video posted by Doug N4H&H on his YouTube channel N4H&H Radio. And the title for his YouTube video is Basic Antenna Theory, and the URL is shown there. And this video is meant to be a deeper dive into the whys for those who might be interested in digging deeper into the inner workings of antennas. And the basic concepts presented by Doug N4H&H are as follows. The open wire feed line does not radiate RF because the electric fields are canceling each other. And he also says to try to match the rig source impedance of 50 ohms to the antenna load impedance whenever possible, and to have an SWR that's less than 2 to 1 and preferably less than 1.5 to 1. And to have your antenna height at somewhere close to a half wavelength if possible. And we'll discuss what the limitations are to having these basic end goals for your use of antennas. And the simple wire antennas considered in this video are as follows: the simple dipole, coax fed, the end-fed half wave, another coax fed antenna with a transformer at the end, typically 64 to 1 or 49 to 1. The doublet, which is fed with parallel wire feed lines and uses a balanced line tuner. And the important thing to remember here is the word parallel. It's important to maintain the parallel distance between the two wires, because that's what is a big factor in the cancellation that happens in the feed line. And that's why the feed line losses are low. Here's an example of a balanced line tuner. The red and black terminals on this QRP tuner are for the balance lines, or the two legs of the feed line. If you're in the shack, you will likely have one of these. This is just an antenna tuner with balanced inputs in the back of it. And lastly, we will consider the random wire fed with a coax and uses a 9 to 1 unan. And an example of such an unan is this matchbox sold by the Emergent Amateur Radio Club of Hawaii, ERCHI. And the simple dipole consists of two quarter wavelength wires that are connected to a center point. The center point has a center conductor that's connected to one of the legs, and the shield is connected to the other. And typically these antennas are the size of the legs are given by the formula 468 divided by f, the frequency, in megahertz, and gives you the leg length in feet. And this is what you typically see in many textbooks, antenna books, and magazine articles. And it's easily derived from the free space formula, except that free space formula is 492 divided by f, as given by 300, the speed of electromagnetic radiation, 300 million meters per second, divided by the frequency, in this case 14.2 megahertz, times the conversion from meters to feet, which is 3.28 feet per meter and a half, to give you the quarter wavelength leg dimension. And the 492 formula will give you a length of 34.6 feet. The 468 formula will give you a length of 32.9 feet. And there's a big discussion, or a deep discussion in the EHM article that shows the history of why that is. Turns out the 468 formula ended up in the ARRL antenna book in the 1930s, and it's sort of stuck until now. It's still in many handbooks on amateur radio. Just to give you an idea what the effects of standing wave ratio are on power lost because of reflection losses, and that power is dissipated into the feed line. At 1.5 to 1, you're losing about 5% of your input power. And then SWR of 2 to 1, you're losing approximately 11% of your input power. And the greater than 2 to 1, the radios start folding back power to preserve its finals from burning up. This slide is meant to give you a better visualization for what's happening in the antenna. The blue plot that's bouncing up and down is the current distribution, both on the antenna and on the feed line. And the red one is the voltage. You can see that the current is maximum at the center point and minimum at the ends. And the opposite of that is true with the voltage. The voltage is maximum at the ends and minimum at the center. You can see also that the feed line, if this was a parallel feed line, that those, the blue and the red are effectively same in magnitude but opposite. And so hence the cancellation that takes place. And that's true up to a point, and we'll discuss those limitations later. Here's another visualization of what's happening, and it's the same, basically the same plot, except it's not showing the electromagnetic radiation. Let me go back briefly to this other plot, and just to explain that as AC current is flowing in the wire, it's also generating radio waves broadside to the wire. And if there was no AC current being fed from the transmitter on receive, any electromagnetic radiation in the form of radio waves that's impinging on the wires will also generate an alternating current in the wires, which is then processed by the receiver into an audio signal that you can hear. And that's why this whole process also works in reverse. Just to give you a calculation for what the voltage is at the center, if you're transmitting at 5 watts, your current is roughly a 1/4 amp, and your voltage is about 19 volts. And at the ends, the voltage is about 125 volts, and the current is about 0.04 amps, so much smaller current at the ends. That's assuming that the impedance at the ends is roughly 3,200 ohms. We know that the impedance is somewhere between 1,800 to 5,000 ohms at the ends. Here's another visualization for the density of the electromagnetic waves that's being radiated by the antenna as the current is flowing in the wire. And the tighter the lines, the stronger in that direction. You'll see that there are very few lines that are radiating in the towards the end of the wire, and the wire is shown by that blue line. And here's what that figure 8 radiation pattern looks like. It's generated from an antenna modeling program like EasyNet. And to read this this plot, the maximum takes place at 0 azimuth. Is that 0 azimuth or is it 90? Anyway, this direction is the maximum direction, and the minimum direction is at right angles to it. And there's a large attenuation in signal strength as you go away from the maximum at roughly 45 degrees from this maximum angle. You're down about 4 dB, and past that you're down about 6 dB or a quarter. The pattern when it's over real ground, this is the elevation pattern now, and the azimuthal pattern when it's over real ground is shown by the this is a picture of a 3D rendition of the azimuth pattern, a half wavelength above the ground in terms of antenna elevation. And so the maximum now is about 45 degrees, and at a higher angle it attenuates, so you get your maximum signal at that point. And every 3 dB is half power, so 6 dB would be a quarter power. So if we do a calculation at 5 watts ERP and half wavelength above ground, at 1 meter, an isotropic radiator will generate about 0.4 watts per meter squared. And a dipole, which is let's say 6 dB above an isotropic radiator, or a 6 dBi, will have 4 times as much power, RF power, and 1.6 watts per meter squared at 45 degrees. Here's what the screens of an antenna modeling program look like, and this is your antenna, and we modeled this antenna at 40 feet above ground level, which is this input and 2, and you see 40 feet, and the radiation pattern is shown by this 3D plot. You can have this plot in 2D or 3D, and there are many inputs in this window here. And I've shown a graphic of what an isotropic radiator looks like. And so horizontal dipoles are very effective antennas when deployed at high enough heights, and high enough heights being somewhere close to a half wavelength. Here's a plot comparing various antennas. They're all dipoles. The red line is a flat top dipole. The blue line, this blue line here with the blue arrow, this is an inverted V, except that it's a 40 meter half wave instead of a 20 meter half wave, and it's an inverted V with a 12 degree rise and a 12 foot rise and 33 foot run. So that's basically the shape of it. And this middle plot here is an inverted V with a 8 feet rise and a 14 foot run, to give you about 17 foot length of radiator. And what this plot is meant to show is that at lower lengths you're actually better off, if you're going to use an inverted V, to use a 40 meter inverted V, or an antenna cut for 40 meter half wave, and use the second harmonic to radiate 20 meter or 14 megahertz RF. So at low heights it's advantageous, and that's why A lot of SOTA operators use the 66-foot or 40 meter band end-fed half-wave antennas even when they transmit at the higher bands, and they just use the higher harmonics, 20 meters being the second harmonic, 15 meters being the third harmonic, and 10 meters being the fourth harmonic. At this point, we're going to have a brief digression into this rabbit hole of why 50 ohms. Why are radios designed with a source impedance of 50 ohms, which makes it necessary for us to use 50 ohm coax? We know that the dipole's load impedance is 70 ohms. So why didn't they standardize to 70 ohms instead of 50 ohms? Let's look at the power transfer using the I²R formula for power. The power transfer is maximum. This is the current portion of this formula, I², and this is the load impedance. That this power transfer is maximum when the load impedance is matching to the source impedance. Of course, the radio impedance is source impedance is 50 ohms, and the dipole is at 70 ohms, so they don't match. So we know we're not having maximum power transfer. And so, but this equation doesn't answer why the source impedance of radios are 50 ohms. We just know that the maximum power transfer occurs when load impedance and source impedance are the same. It turns out, if you do a Wikipedia search, that the Beck's coaxial cable impedances in high power, high voltage, and low attenuation applications were experimentally determined by Bell Labs in 1929 to be 30, 60, and 77 ohms respectively. For coaxial cable with an air dielectric and a shield of a given inner diameter, the attenuation is minimized by choosing the diameter of inner conductor to give a characteristic impedance of 76.7 ohms, or what we might be considered now to be close to an RG6, which is 75 ohm coax. Remember, this is not RG6 though, this is an air dielectric. The RG6 cable had not been invented yet. At the time, when they also say when more common dielectrics are considered, the best loss impedance drops down to a value between 52 to 64 ohms, and the maximum power handling is achieved at 30 ohms. So this appears to be some sort of a compromise between 30 ohms and 77 ohms. Well, it turns out that 50 ohms is roughly, and if you look at both the arithmetic mean and the geometric mean between these two numbers, 30 and 77, you get somewhere between 53.5 ohms and 48.1 ohms. So if you compromise even between the arithmetic mean and the geometric mean, you come up with 50 ohms. So the key takeaways here is that the 50 ohm standard was established back in the 1930s before having invented RG6 coaxial cable. And they standardized to a source impedance of 50 ohms to be a compromise for best reception and best power handling. So the takeaways here: if your amateur radio application is either shortwave listening or a receive only, like putting up a beverage antenna or a Waller flag, then 75 coax is the one to use. That gives you the least attenuation of your signal because you're only receiving anyway. For transceivers that are transmitting at high power or close to legal limit, it is desirable to make the antenna system to be close enough to 50 ohms and as close as possible for maximum power transfer, because we are stuck with a source impedance of 50 ohms decided and agreed upon by the radio manufacturers a long time ago. Would 75 ohm transmission lines also work? Is a question. It will if care is taken in impedance matching the lower power applications using some sort of an antenna tuner or a custom design transformer, and you'll have the advantage of better signal on receive. You won't have ideal power transfer, but 75 ohms is close enough. If it doesn't make that much difference under low power applications. And now that we'll leave the 50 ohm question. We know now that the 50 ohms was based on a compromise, and that's why we're stuck with it. Now, in terms of minimizing SWR to that 50 ohm standard, and we're looking now at a dipole, or any kind of an antenna for that matter. A quarter wave vertical reaches maximum efficiency at a load impedance of 37 ohms. And a dipole reaches its lowest SWR point. It never gets down to 50 ohms. The lowest SWR point, given some assumptions, is closer to 40 feet, load impedance of 58 ohms. And at half wavelength, it's 73 ohms, round about 70 ohms. So in either of the above cases, the antenna gives you maximum gain at somewhere above 50 ohms, both a vertical and a dipole. So it's not necessarily better to get to 50 ohms. So you would have to consider both where your antenna is more efficient at, and what and to make sure that your radio is happy enough, and the word is happy enough, with the reflection losses, and that the reflection losses are acceptable to not damage the finals. And as long as the SWR is below 1.5, the radio is happy. Now let's look at parameters that affect antenna performance. And the picture shown is that of a heliax, which is a coaxial cable that is large and heavy, but it's very low loss. So impedance matching to the transmitter for a low return loss will maximize RF radiation. So that's number one on our list. Number two, minimize ground losses. So for horizontal wires, that is to make the wire high enough above ground, half wavelength, and for verticals to have a good ground plane. And for your flat top antenna, the gold standard is the half wavelength rule, and for quarter wave vertical, it's the 60 to 120 quarter wave ground radials is sort of the gold standard. And to make sure that your feed line losses are tolerable, and of course this is a compromise, you can have a very low loss but heavy and expensive heliax, or you can have a very lossy but very light and portable RG174. And RG8X is a reasonably good compromise between the two. Wire feed lines have low loss when properly matched to the radiator, and we'll get into that in a later slide. Ground plane parameters, ground conductance, and dielectric constant are site-specific and not really, you can't really control it, because wherever you set it up, you're sort of stuck with site conditions. But if you're not stuck with it, like you're going an expedition where you can be near ocean, like a beach, ocean salt water is a big performance booster, especially for verticals. And if you set up your antenna over a marsh, salt marsh, like in the near Charleston, where there's some salt marshes, then you're getting a very good ground plane for your antenna. And it will also help even a horizontal wire antenna. The thicker the wire, the more bandwidth you get, and there's also less ohmic losses from heating, the I²R heating of the wire. So, and this is not as important as the other ones. It's probably the least important of these 6 parameters. The next antenna we're going to look at is the end-fed half-wave. It has been used for many decades now. It's a clever way to achieve multi-band performance because resonance occurs in integer multiples of the fundamental resonant frequency. It is also a half-wave antenna like a simple dipole, and the antenna configuration orientation can be just like a dipole. It can be a flat top, it could be an inverted V. You can also configure it to become a vertical. We can use a switch to bypass the coupler, since you'll be using the coupler, and then connect it to a ground plane to make it a quarter wave vertical, if you wish. It does need a transformer to match the high impedance at the end of the half wave, and this transformer will dissipate some power, so you'll have some inefficiencies because of the presence of a transformer. But with a properly designed transformer, this can be very small. And at the higher power levels, the counterpoise is a good idea to have, as to give a dedicated path for the currents, which are low to begin with, but it gives it a path so that it doesn't use the feed line as the counterpoise. Steve Yates, AA5TB, has given a good framework for understanding end-fed half-wave antennas. Well, getting back to the discussion of the end-fed half-wave antenna, and here's a graphic of a schematic of an end-fed half-wave antenna with no counterpoise, and it says on the bottom part of this slide that this theoretically will not work. However, it does seem to work in practice, and there's been some discussion as to why it does work, and we'll go into a little bit into that discussion. Many manufacturers have been selling QRP transformers without counterpoise lugs for years, and I myself have conducted many summits on the air activations without using counterpoise. So that theoretically will not work, in practice still works. So the schematic is more correct in having a counterpoise return. Of course, it's not necessarily a half 1/20th of a wavelength as proposed by Steve Yates, AA5TB, but in reality, even when we claim there's no counterpoise, there is a counterpoise. and more than likely it is the feed line that's being used by the antenna as a counterpoise. And the reason it all works is because the currents are low. And because the currents are low, it's not giving problems in using the feed line as a counterpoise. For higher power applications, it would be beneficial to have a dedicated counterpoise. And Steve Yates A5TB has determined that 1/20th gives a zero reactance component, which is, in his case, his claim that it should be about ideal as a counterpoise length. So for 40 meters, that would be about 2 meters long. And so that's why when I make my antennas, I have a dedicated counterpoise lug even for QRP. So it gives the option for the operator to actually put a counterpoise there if he chooses to do so. And you can visit some of these antennas of mine at www.ny4gefhw.com. And using a case study for a 20-meter end-fed half wave using an antenna program like EasyNet, one can generate some predictions for performance and both in terms of gain, antenna gain, and also in terms of standing wave ratio for a particular length of wire that you've selected. And here's the SWR plot, and here's the gain plot, and you have the typical lobe. This happens to be at 40 feet. At 40 feet, you get this lobe that goes straight up, but you get more gain and lower radiation angles compared to the half wavelength height. This is a little bit over half wavelength. It's 40 feet. Half wavelength is roughly 34, so it's 6 feet above the half wavelength height above ground. So the bottom line is these half-wave antennas can be very good performers. And when you cut the antenna for a lower band, like 40 meters or 80 meters, you get the benefit of getting resonances of the fundamental harmonics of the fundamental. For example, if your fundamental is 7 megahertz, you get a resonance at 14, 21, and 28. And in most cases, you can have it all. Those resonance will give you some acceptable level of performance even without a tuner for all those bands. Now, if you configure your end-fed half wave as an inverted V, you can get still reasonably good performance. You don't get as big a gain in this direction as the one at 40 feet, and you don't get performance also as compared to a flat top half wave wire, but it's still a decent performer. You lose about 1 dB as long as you keep the apex at about half wavelength. SWR is still pretty good. Now this is the case of a low sloper with the apex at less than half wavelength. In this case, the apex is at 20 feet, and you can see that the pattern that emerges is near NVIS, and at the 45-degree angle, radiation angle, you're down about 3 dB. So it's not as good a performer as the inverted V at half wavelength at the apex, or a flat top that's half wavelength above ground. A good solution to overcome this is instead of using an end-fed half wave cut for 20, is to use the end-fed half wave cut for 40 and then radiate it on the second harmonic, being the two half lobes for 20 meters, and you get better gain, much better gain in those directions at 45-degree angle. And I have a model for that I've evaluated. I'm not showing it here, but non-coax fed dipoles is the next subject, doublets. And what we're going to consider here are doublets that are fed with parallel wire feed lines. There's the 450 ohm window line, a 300 ohm twin lead, and the 600 ohm ladder line. And examples of these are NorCal doublet, ladder line doublet, and G5RV and ZS6 BKW, which is sort of a special doublets here. The NorCal doublet is made from 4-conductor computer ribbon cable with 22-foot length radiators with a 28-foot feed line. The G5RV is got a 34-foot window line and has got a 51-foot radiator per leg. The ZS6 BKW has a longer feed line. It's 41 feet, but the radiators are shorter. It's like 47 feet. I didn't put this on this slide. And of course, W4RLN, who's now SK, is a big espouser of the all-band doublet using ladder line. Of course, these require an antenna matching unit, or maybe a transformer or both, to get the impedance near 50 ohms. High SWR is presented to the radio end, so you need some sort of a tuner to match it. Losses in the wire feed line are low because the cancellation that takes place in the wire feed line, as long as this SWR is not overly high. And you can use experimentation to optimize wire feed line length and avoid having the wire feed line touch the ground or be near metallic objects. Here's a special study that was done and documented in a 2004 QST article about what losses can be expected from wire feed lines. And this is a 100-foot test dipole, and they looked at it from all the bands from 160 meters all the way up to 10 meters. And you can see that the SWR is and the losses associated with SWR is only really bad for 160 meters. It's probably borderline on 80 meters and okay from 40 meters on up, where the losses are close to less than half a dB. In most cases, less than 0.2 of a dB. And these are my measurements for SWR for a NorCal doublet as it's presented to the tuner. This is before the tuner. And you can see that on 80 meters it's borderline. On 60 meters it's okay. It's too high on both 40 and 20, which makes me question the value of this on these money bands. But on 17, 15, and 10 meters, it's actually okay. I found that I can tune 20 meters with my ZM2 balance line tuner, but I'm not sure. I think this is suggesting that my losses from SWR are probably high enough that I will not be happy with the results. Now, radio amateurs have employed two ways. Let's go back. Two ways that you can connect this to a radio. The radio would be on the left here, and this is the tuner. And before the balance line connection to the antenna is a balun. This is one way to do it. This is configuration A. And the more efficient way to do it is to have a remote tuner that's close to the antenna, and then connect that to a balun, and then have the coax go to the radio. This way, the coax is not seeing, and the imbalance line, which is the coax, is not seeing any of the high SWR. So you will have very little loss because of SWR loss in your coax. This is from the same 2004 QST article. And this is comparing the G5RV and the ZS6BKW, and they're really close cousins to each other. The only difference is the length of the radiator and the feed line. And you can see that ZS6BKW has more bands that are usable without using a tuner than the G5RV. You have 40 meters, you have 20 meters, you have 17 meters and 12 meters, and 10 meters is borderline acceptable. You still need a tuner for 15 meters and 30 meters, and of course 80 meters. And lastly, we'll be discussing the end-fed random or long wire antenna. And the ironic thing about this is that the length of the antennas are anything but random, and the term random is a misnomer. The wire lengths that are to be avoided are multiples of a half wave or a half wave, which eliminates a lot of lengths. What happens when the wire is a half wave length, then at those points the SWR that results are not really workable at the amateur bands that you're interested in. When these lengths as suggested by VE3 EED are chosen, like 29, 35, 41, 58, 71 feet, and so on, then when you use a 9-to-1 unun to transform the voltages in the SWR, it's something that can be easily matched by an external tuner, and it doesn't have to be a wide range tuner. It can be matched by it. And because they're end-fed, the coax lengths are shorter and thus less loss. Examples of 9-to-1 ununs that are commercially available are the ones sold by Emergency Amateur Radio Club of Hawaii, ERCHI, and then the KX3 Helper is another one that's good to 100 watts. And these 9-to-1 ununs are easily home-brewed. There are plenty of plans on the internet for making these. And of course, these ununs are not one size fit all in terms of power handling. You have to be careful that you don't overpower an ERCHI transformer by putting 100 watts to it. It'll burn it up. Now, in final thoughts and my experience, I seem to have a bias for resonant antennas. That's just not sure. I'm not saying that if you use any other kind of antenna, it's wrong. That's just my bias. And that's what's worked for me. And in my radio experience, I've used them all, but I use resonant antennas. And even my 160 meter antenna is also a resonant antenna. It's a dedicated quarter wave vertical that's in the configuration of an inverted L over a K2AV folded counterpoise, which I used in CQ Magazine DX Marathon back in 2017 that I entered for the 160 meter band. I did well enough to place 7th. I believe I worked about 118 DXCC entities that year. And I've used a hex beam for many years. I've had a hex beam deployed since 2012, and in 2016 I entered the CQ Magazine DX Marathon. I placed 6th that year, and which is just one short of 5th place, one QSO short of 5th place. To I believe I worked 200 or so DXCs. I can't remember now. It's been so long. Of course, I've used end-fed half-wave antennas for summits on the air almost exclusively. Maybe once I used a dipole, a straight-up simple dipole, but for the most part I've used end-fed half-waves. And I've used a stepper crank IR for an expedition I made to St. Pierre and Miquelon back in 2015. And that's a resonant antenna too, and uses a couple of cranks to change the length of the radiator, and to change another crank to change the length of the counterpoise, and it uses a single elevated radial. I've also used receive antennas like K9AY and Beverage on Ground. And so antennas for me are kind of an obsession, and I guess the watchword that I want to convey to you is experiment and learn. And it can be a lot of fun, and it can be a rewarding experience. And if you have any comments or questions, please leave them in the comment section of this video. And I do thank you for staying and watching this to the end. Rather lengthy video on antennas.